One of the most intriguing endeavors in all of science is to find out whether we are alone in the universe. While the sheer number of stars in the observable universe suggests that we're most certainly not unique, we do have to find evidence for the existence of alien life, so that probabilistic assertion becomes a scientific one. Of course, finding evidence for extraterrestrial life is way easier said than done, and will be an extraordinarily difficult task for astrobiologists due to the vast space between star systems. But fortunately, science has advanced so far that there are ways to tell if life exists elsewhere without ever having to visit distant alien worlds. Before we can begin to imagine the exciting stuff, which are intelligent aliens on far-off exoplanets, we first have to look for evidence on our cosmic backyard. The solar system reveals a stunning diversity of worlds, from charbroiled Mercury and Venus to the frozen outer reaches of the Oort cloud. In between are a few tantalizing prospects for life beyond Earth. Maybe subterranean Mars or the moons of giant planets with their hidden oceans, but so far it's just us.
We can now think of classes of star systems. And is our solar system average? Is it weird? How many do we have in the Goldilocks zone versus these other systems? So you can start twisting your way into the questions you can now ask. Are there planets that orbit other stars? Are there planets like Earth that orbit other stars? Are there planets that, like Earth, orbit other stars that are in the Goldilocks zone? We got that. Might those planets have life? That is the current frontier. There's a way to decide whether they have life without going there. So in these planets, they're on a frontier. It's a cottage industry in astrophysics today, where if the planet moves in front of its host star, the light from the star will pass through the atmosphere, come out the other side, and the chemistry of the atmosphere will lay a fingerprint into the light of the star. And it turns out, unlike what we had ever imagined before, we look for what are now called biomarkers in the atmospheres of those planets, which would tell us if we were going to pick one to visit, what might most likely have biology that we are most familiar with.
On Earth, life leaves telltale signs in the atmosphere. Photosynthesis is ultimately responsible for the high oxygen levels and thick ozone layer. Microbes emit methane and nitrous oxide into the atmosphere, and seaweeds emit chloromethane gas. These chemicals, when present in sufficient quantities, are indicators of life and are known as atmospheric biomarkers. Detecting them in the atmosphere of an exoplanet should, in theory, be a means of discovering whether life exists on any alien worlds. While biomarkers have never been spotted in observations of an exoplanet because their signal is so faint, the new generation of telescopes being planned today may be sensitive enough to detect them. Chemicals in a plant's atmosphere affect light that passes through it, leaving characteristic chemical fingerprints in the star's spectrum. Using this technique, astronomers have already deduced a wealth of information about the conditions present in large and hot exoplanets. Biomarkers would be detected in much the same way, but here the signal is expected to be so weak that scientists will need a solid understanding based on theoretical models before they can hope to decipher the actual data. If we're ever able to find evidence for alien life, our best guess is that it will be carbon-based. The kinds of living organisms currently known on Earth all use carbon compounds for basic structural and metabolic functions, water as a solvent, and DNA or RNA to define and control their form. If life exists on other planets or moons, it may be chemically similar, though it is also possible that there are organisms with quite different chemistries. The possibility of life forms being based on alternative biochemistries is the topic of an ongoing scientific discussion, informed by what is known about extraterrestrial environments and about the chemical behavior of various elements and compounds. The element silicon has been much discussed as a hypothetical alternative to carbon and as the basis for an alternative biochemical system, because silicon has many chemical properties similar to those of carbon and is in the same group of the periodic table. Like carbon, silicon can create molecules that are sufficiently large to carry biological information.
The reason why people suggest silicon, there's a good chemical reason for this. Silicon appears directly below carbon on the periodic table. We are carbon-based life. So if you are vertical on the periodic table, you may remember that you have the same configuration of your outer electrons, which means you make the same kinds of molecules chemically as everybody else above and below you. So if carbon can make life, surely silicon can as well. But yeah, you can make the similar molecules, but some properties are different. If you make silicon, bind it with oxygen, what's called binding energies are different. So whereas if your molecules based on carbon, you can hang together pretty good, but if there's an assault on the environment, you break apart the molecule, and then there's more experimenting to go on. This is how we grow the diversity of life on the Earth, not by having rock-hard molecules to make your life. So silicon, in principle, you could do it, but it's not clear that you'd have the experimenting in nature that is required to find self-replicating life that then creates a diversity. Carbon is more abundant in the universe than is silicon, by a factor of 5 or something. So you don't even need to appeal to silicon because carbon is there for you. And if you've got the carbon and you can make more kinds of molecules with carbon than any other kind of molecule, then we're good to go. So I'm okay thinking that life elsewhere is based on carbon. Pick an atom to base life on. Carbon is your atom. So in the universe, you might expect carbon.
NASA has announced that our next destination in the solar system is the unique, richly organic world Titan. Saturn's largest moon is an icy world whose surface is completely obscured by a golden, hazy atmosphere. Titan is the second largest moon in our solar system. It is the only moon in the solar system with a dense atmosphere, and it's the only world besides Earth that has standing bodies of liquid, including rivers, lakes, and seas on its surface. Titan is also thought to have a subsurface ocean of water. Advancing our search for the building blocks of life, the Dragonfly mission will fly multiple sorties to sample and examine sites around Saturn's icy moon. Dragonfly will launch in 2026 and arrive in 2034. The rotocraft will fly to dozens of promising locations on Titan looking for prebiotic chemical processes common on both Titan and Earth. Dragonfly marks the first time NASA will fly a multi-rotor vehicle for science on another planet. Dragonfly will explore diverse environments, from organic dunes to the floor of an impact crater where liquid water and complex organic materials key to life once existed together for possibly tens of thousands of years. Visiting this mysterious ocean world could revolutionize what we know about life in the universe.
Does life require liquid water? Maybe all it requires is liquid. On one of Saturn's moons, Titan, it is so cold on Titan, methane has liquefied and it has become lakes and rivers. There are meandering rivers and river deltas on Titan of running methane. So now we imagine life on Titan with methane as the fluid that is carrying nutrients from one part of the creature to another. I will not rule that out. And if that's the case, then this whole concept of a Goldilocks zone has to be revisited. Because you could have a methane Goldilocks zone. Pick your favorite chemical and imagine life that way.
Through the study of astrobiology, NASA invests in understanding the origins, evolution, and limits of life on Earth. This work has been important in shaping ideas about where to focus search efforts for life. As NASA explores the solar system, our understanding of life on Earth and the potential for life on other worlds has changed alongside the many discoveries. Besides our solar system, NASA is exploring ways to help us answer fundamental questions about life beyond our home planet. Identifying Earth-sized planets around distant stars, NASA's science missions are working together with a goal to find unmistakable signs of life beyond Earth. As of August 2021, there are 4,800 confirmed exoplanets. NASA's first planet hunting mission, the Kepler Space Telescope, paved the way for our search for life in the solar system and beyond. An important part of Kepler's work was the identification of Earth-sized planets around distant stars. After 9 years in deep space, Kepler collected data that indicates our sky is filled with billions of hidden planets, more planets than even stars, making us wonder if or when we will be able to find evidence for alien life. Thanks for watching. Did you like this video? Then show your support by subscribing and ringing the bell to never miss videos like this.